Alright, so for this problem, for this section, we're going to go over properties of definite integrals. And what you're going to find is that these properties are pretty much exactly what you'd expect. It's very similar to the way we did this for indefinite integrals, and a lot of it resembles what we saw in derivatives. But there's a little bit of new tricks here. So we've normally thought about closed intervals from A to B. But we can actually, instead of having a lower bound strictly less than an upper bound, we can even do interesting things like letting the lower and upper bound be the same number, or letting the lower bound actually be a larger number than the upper bound. And those are all valid things to do, and there's a little bit of hand waving that happens underneath that has to do with the way that the Riemann sum gets permuted so that's possible to happen, but it's not so big of a deal, and so for practical purposes we're not going to go deep into why that happens. But some of the more interesting things are like this one. If the lower and upper bounds of integration are the same, the value of the integral is 0. And this makes intuitive sense. If you think about it in terms of like an area, if you have a 0 width, well, 0 width times whatever height, doesn't matter, is automatically 0. So it just smashes it to 0. The second one is probably a little more unintuitive, but if you have a standard integral from A to B and you flip the limits of integration, you get a negative sign. So why is that? Well, think about it this way. If I'm starting from A and I'm moving to B and I'm sort of generating area, I'm sort of, think of it like interest in an account, right? I'm gathering interest as I go from A to B. Well, if I started at B and I went back to A, I'd be like losing interest. So if I thought this was 0, I'd be losing. So it'd be negative relative to where I start versus positive to where I start. So that's the idea. If you flip the limits of integration, you induce a negative. The next one is a very simple situation. If I have a constant k in the multiplied by a function, I can pull that out and evaluate the integral without it. So I just pull a constant out. So that was true of indefinite integrals and true with derivatives as well. Similarly to indefinite integrals and derivative, if f and g, now you have to be a little careful. F and g have to both be integrable here, but if f and g are both integrable, then you can integrate them separately. If you have some sort of jumble of terms, you can split them into separate integrals, evaluate them, and then whatever operation was between them, whether it was a plus or a minus, stays with it. Another one, this is also very intuitive. If one function is less than or equal to another on the whole strip, right? So if you have two functions and one's always below the other, then the value of its integral must be less than the value of the other one's integral. And that makes intuitive sense because as you're adding up those pieces, those rectangles, if one's rectangle is always taller than the other, well, the sum of those rectangles are going to be taller than the other, or the sum of those areas is going to be larger than this one's going to be larger than that one. Ugh. And finally, you have a piece about if you have some number between A and B, then you can actually, if it's integrable on AB, then you can split it up. So from A to C and C to B, and then it may seem odd. You may want to go A to B to C, but you're going from A to C and C to B is here. Why do you want to do that? Well, usually what happens isn't this. It's like I've got an integral from 1 to 2, and I've got an integral from 2 to 4. So I can smash it together and just say the integral from 1 to 4. So I don't have to evaluate two definite integrals separately. That's a pretty common thing. There are other reasons that you actually want to go the other way. You may have certain things you want to exploit about the way those behave, but that's beyond the scope of what we want to do right now. So what we're going to do is we're going to put these properties to use here. We're going to say, given that we know this integral is 20, this integral is 4, and this integral is 2. Notice I have an x cubed, an x, and just a dx. So in this case, this would be like 1 dx. Given that information, we want to find these values. So in the first case, it looks like this, except it's 3 to 1, it's not 1 to 3. So if we look over at property 2, what that tells me is that it induces a negative. So that's going to be the negative version of 1 to 3 x cubed dx, which then is negative 20. So then coming down here, I have that 1/4. Well, oops, that's black marker. Let's do a red one. So what property 3 tells me is that I have a constant multiple, so I can pull it out. So that will give me 1/4 integral of 1/3 x cubed dx, which is 1/4 times 20, which is 5. And then finally, I have x minus 5 dx from 1 to 3. So I can use property 4 here, and I can say, well, that's the integral from 1 to 3 of x dx minus the integral from 1 to 3 of 5 dx. And then I can use property 2 to say that's the integral from 1 to 3 x dx minus 5 times the integral from 1 to 3 dx. So then I can use that's 4 minus 5 times 2, giving us negative 6. And so in that way what we do is we leverage kind of a table of values and use our properties so that we don't have to reevaluate that integral each time.